This is section 3.5 for precalculus. And in this section, we're going to be using our knowledge of exponential and logarithmic functions to talk about exponential growth and decay and modeling data. So and learned about exponential and logarithmic functions and then turn that into solving exponential and logarithmic equations. And we're going to see how that can actually model some real life data in this section. So these are our learning objectives. Please take a look at those. These are the examples we're going to solve. And then a little knowledge first. Exponential growth or decay. So exponential growth is simply like an exponential function, right? A equals a naught e to the kt. So a sub 0, we say a naught e to the kt. So this is a function of time, t. A naught is your initial amount in your population at time 0 when we start the clock. And then you have growth that is exponential as long as k is bigger than 0. Okay, so in other words, we have growth that is growing without bound as long as k is bigger than 0. If k is less than 0, we have e to the minus kt. T is time, always positive, so we have exponential decay. The amount in the population is dying off with time. Okay, so that's how that exponential growth or decay works. So in example 1, let's say we have an exponential growth problem where we have a equals 108.3 times e to the 0.012t. And let's say that's the population of a country in millions. So whatever answer we get here is in millions. T years after 2003. When will the population be 150 million? So we do know this is exponential growth because k, 0.012, is positive. So if you want to know when that will be, it's saying what time t, right? Remember, time 0 is 2003. So you need to figure out what t is and add that many years to 2003. So how do I solve for t? Well, 150, because remember everything is in millions, so we'll leave it as 150, equals 108.3 e to the 0.012t. And we need to solve this for t. So what we have is we have an exponential equation. Right? I can divide both sides by 108.3 and I get e to the 0.012t equals 150 divided by 108.3. I certainly can't write 150 over 108.3 as e to the something. I have no way of doing that, so I have to introduce logarithms. It's certainly important to definitely introduce a natural log at this point. When I have a base of e, the natural log is log base e, and e to the something times t is an exponential function with base e. So in this case, you wouldn't have to, but it's certainly the easiest thing to do is to use the natural log. Take the natural log of both sides. That allows us to bring the exponent down on this side, 0.012t. So I have 0.012t times the natural log of e. Well, this is the reason I use natural log because, again, natural log of e is log base e of e, which says e to what power equals e. So that's 1. The natural log of e is always 1. So 0.012t times the natural log of e technically, which is just 1, equals the natural log of 150 divided by 108.3. This is all just put into your calculator. How do I solve for t? Divide both sides by 0.012. So this is the exact answer. When you put that into your calculator, you get 27.14. So if I round that off to 27 as far as number of years, the year will be 2003 plus 27, because remember times 0 was 2003, so 2003 plus 27, that's 2030. As a second example, let's say we have an artifact which originally had 20 grams of carbon-14 present. So this is an example of carbon-14 dating. We know with carbon-14 that it decays with this growth rate, negative 0.000121. So K is your growth rate. Since it's negative, that's decay rate. That describes the amount of carbon-14 present after T years. So how many grams of carbon-14 will be present in 8,243 years? Right? It initially had 20 grams. So there's your initial amount, right? A0 is your initial amount, 20. E to the minus 0.000121 times T is in years, 8,243 years. Put all that into your calculator, and you get 7.38 grams will be present after 8,243 years when we started with 20. Part B of this example says, well, what's the half-life of this artifact? Maybe you've heard that term half-life before. It means how long does it take for half of it to decay? So we had 20 initially. That means we want to know when is there T left. When is there 10 left? So that means 10 would be equal to our exponential decay model, 20 e to the minus 0.000121 t. And we want to know what's t when this is the case. When do we end up with 10? What is t? So divide both sides by 20. 10 over 20 is 1/2 equals e to the minus 0.000121 t. Take the natural log of both sides because we have a exponential base of e, so that the log base e is the natural thing to do. So we take the natural log of both sides. Natural log of 1/2 equals natural log of e to the minus 0.000121 t. Bring that exponent down in front, which is minus 0.000121 t. Technically, it would be times natural log of e, but we just discussed how natural log of e is 1, right? Log base e of e is 1. Okay? So now you solve for t. Natural log of 1/2 divided by minus 0.000121 equals t. Looks like that'd be a negative number, but the natural log of anything between 0 and 1 is actually negative, if you remember the graph of the log function. So this turns out to be 5,728.5. In other words, it takes 5,728.5 years for half of carbon-14 to go away. So 20 grams would go down to 10 grams in 5,728.5 years. Then 10 grams would go down to 5 grams in another 5,728.5 years, etc. That's what half-life is all about. Okay, so exponential growth is often not the best thing because if you think about it, we can't exponentially grow forever. Think about humans on Earth. If we had exponential growth of humans, we would run out of resources pretty quick. So there are actually better models. These are called logistic growth models. So this is probably the most simple of them. A equals C over 1 plus A e to the minus BT. So the A and the B are all both greater than 0, and C is also greater than 0. These are all constants, okay? So you would never have to figure these out. These would be given to you. But the way this works is, when t is small, you have some increasing, almost exponential type growth. Then we get to a point where resources are pretty much good. But then once you get past that point, we start seeing scarce resources, which causes the growth to start to die off. We have a decreasing rate of growth that then becomes asymptotic, right? We have an asymptote here at some value. And what happens is t goes to infinity. This term goes to 0. As t gets really, really big, this gets really close to 0. So this becomes c over 1. So this asymptote is actually at y equals c. In other words, c is like the limiting amount that we can get to, the limiting amount that the population can get to. Okay, so for example, here we have a logarithmic growth model that says p of x is 90 over 1 plus 27e to the minus 0.122x. This models the percentage, so p is a percentage, p of x, of Americans who are X years old with some coronary heart disease. At what age is the percentage of some coronary heart disease? At 25%. In other words, at what age is about 25% of the people going to have coronary heart disease? So we just look at setting the p of x equal to 25 because remember this is 25. This is in percentage, I mean. So 25 equals 90 over 1 plus 27e to the minus 0.122x. So x is the age. So we need to solve this for x. So the first step is to multiply both sides of the equation by this denominator. So that makes 25 times 1 plus 27e to the minus 0.122x equals 90. Divide both sides by 25 then, and I get 1 plus 27e to the minus 0.122x equals 90 divided by 25. Subtract 1 from both sides in the next step. Right? Subtract 1 from both sides. 90 over 25 minus 1 is 65 over 25. 1 is 25 over 25, so you get 65 over 25. Then divide both sides by 27. So e to the minus 0.122x equals 65 over 27 times 25. And I finally have it in the form of an exponential function. E to some exponent, which has our variable, equals a constant on the right-hand side. Again, I'm not going to be able to write this 65 over 27 times 25 as e to the something. So I'm going to use the logarithm, and I'm going to use the natural logarithm because I have a base e. So the natural log of e to the minus 0.122x equals natural log of 65 over 27 times 25. And the reason we did that again is to bring that exponent down. So this minus 0.122x will come down in front, which means right over here. And then I have technically natural log of e right here, but we know natural log of e is 1. So minus 0.122x equals natural log of this number. So divide both sides by minus 0.122, and here's x. This is x exactly, if you'd like to know what it is. In terms of an age, that's easier to understand. Just plug all this in your calculator and you get 19.18. In other words, at about age 19, about 25% of people have some coronary heart disease. Whoops, I went too far up, right here. At age 19, about 25% of people have some coronary heart disease. Notice our limiting age here is 90. So at age 90, our limiting percentage is 90%. Sorry, not age. So as the age gets really, 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 really old, then about 90% of the people would have some coronary heart disease. And then as the last example here, let's say we have an ancient artifact which contained 25% of its original carbon-14, and we want to estimate its age. So this is called, again, carbon-14 dating. So about 25%. That means that A divided by A naught, its original amount was A naught. About A divided by A naught is 1/4, right? The amount that we have now divided by the original amount is 1/4 because that's 25%. So we don't really know, we don't need to know what was there originally to answer these kinds of questions. We just know that this A divided by A naught, when I divide both sides by A naught, is 25% or 1/4. Set that equal to what's left on the right-hand side, e to the minus 0.000121t, and we have an exponential function that we need to solve for the unknown variable t. That's our age that we're looking for. Again, I have to introduce logarithms because I can't write 1/4 as e to the something. So I introduce logarithms. The reason I do that is to get this exponent down. And then that's that exponent times technically the natural log of e, but again, natural log of e is 1, so we don't write it. Divide both sides by this minus 0.000121. So t is this value. Again, that looks like it's a negative value. We know time is not negative, but it's not negative because the natural log of 1/4 is a negative number. Anything between 0 and 1, the natural log of that is negative. So plug that into your calculator and you see that that's 11,456.98 years old.